Our pendulum design features two 3D printed connectors, fitted with a ball bearing on either end. The connectors are joined together using a 3D printed spacer. As you can see, this allows for free rotation on either end of the spacer. We pass a bolt through the ball bearing on top and fix it using nuts on either side to prevent the pendulum from wobbling about its fixed point of rotation. The bolt is then clamped to the end of a table.
We now demonstrate the operation of this constructed pendulum. While the system does display characteristic behavior of a double pendulum, we note that the system loses energy rather quickly, due to the comparable masses of connectors and the ball bearings. As a result, we cannot approximate these as point masses joined by a massless rod. Analysis was tested against a model of this kind, with a point mass double pendulum model in Mathematica, and a significant discrepancy was observed.
For this reason, we had to update our model, as our assembled pendulum is an instance of a double compound pendulum, with masses fixed at either ends. In stark contrast to the point mass model, the compound pendulum model asserts that the rod itself is an object oscillating in space. After deriving the Euler-Lagrange equations for the system, we arrive at the following equations of motion. We then conducted various tests to determine the influence of changing the launch angle of the connectors on the motion of the pendulum system. In the first case, where the first connector is at a launch angle of 90 degrees and the second at a launch angle of 0, we see that the compound pendulum accurately models the empirically observed motions. We know that as time progresses, the real-world pendulum loses energy due to damping and thus strays from the theoretical prediction.
In the next case, both connectors are released at an angle of 90 degrees. At these conditions, we expect each of the rods to display characteristic singular pendulum behavior. This is observed in the actual model, and the strong agreement with the theoretical predictions demonstrates the efficacy of our pendulum system. In this example, we can clearly see the effects of damping in the compound pendulum system. In the third case, both the connectors are released at an angle of 180 degrees as seen. In this case, the motion of the real-world model does not fully match that of the prediction. This is likely due to the higher stress being put on the bolt clamp system in this case, which causes it to wobble under the clamp. Thus, the assumption that the pendulum was fixed at a point was potentially violated. Additionally, part of the energy of the loss of the system can be attributed to this motion.
Finally, we take a look at the case where the first connector is released at an angle of 180 degrees, while the second is at an angle of 0, causing it to overlap with the pivot of the system. Similar to the previous case, the system is sensitive to initial release angle and may fall in either direction depending on the method of release. We observe good agreement with theoretical results after accounting for the energy loss due to damping, which causes the system to undergo similar oscillations with smaller amplitude. Some of the possible deviations between theoretical and empirical results are due to potential errors in our system. While efforts were made to ensure the release angles were accurate, the connectors were physically released in each trial, and so there is bound to be some error in this. In the future, the launch angle can be set and released precisely using a mount or electrical piston, allowing the pendulum to be released without any additional applied force.
Additionally, the tracker software was used to measure the position of each ball bearing as a function of time. This is a manual tracking software, hence the position of each ball bearing had to be selected frame by frame. This induces potential error, as the exact same region of the ball bearing may have not been selected each time. The camera had been set up parallel to the experiment to reduce the potential for parallax error. However, in actuality, this parallax error is likely to still persist in some way or form. Another potential error in the design arises due to the imperfection in the system of attachment of the pendulum to the table using a bolt and a clamp. As mentioned earlier, greater release angles and greater gravitational potential energy causes a large jerk about the bolt, which may result in the bolt wobbling, thus introducing error in our experiment due to energy loss.
We note the predictions themselves have uncertainties that arise from the measurements of the weights of the connectors and bearings and the lengths of the connectors. We see from the data recorded that the measurements agree well with theoretical predictions within the effects of damping. For larger release angles, data recorded does not resemble the ideal predictions as closely for the reasons mentioned before. Finally, we end this report by displaying some of the chaotic motion the system undergoes when released with some initial velocity.
Construction of this double pendulum system was a fun and enjoyable task for our HPO project for Physics 2. Thank you so much for watching, and if you liked the video, make sure to leave a like down below. Thank you. Goodbye.